I'm here for the new job.
Okay, here they, oh wait, one second. Hi.
Hi.
Okay, wait, they're not there yet. They're about to be there. Okay, here we go. Wait. Okay. Okay, here we, wait, don't press that. Oh, wait, yeah, just leave that. Okay, ready? Here, they're gonna come.
Wait, whatever I do on the iPad, you do? On the computer?
Yeah, it shows up, whatever's up.
Mhm.
Hello, there, okay. Hello, hello. Hello, you want to say hello? Say.
Hi. Daddy is not here. Hey, I won't.
Hello, hello.
Daddy, why whenever I turn left with my head, the screen turns right?
Oh, good question. Yeah, because it's
Ding dong.
good question.
Hello. Hello. Daddy, where are you? Daddy, can you change the background?
I can't right now, and I should start teaching you in a minute, but say, I don't know if they, hello, hello. Oh, wait, can we hear them?
Hi, Professor.
Oh, hello. All right, thank you. So we can hear them. All right. Hello.
Hi, I'm the junior professor.
Yes, that is true. He is the lab tech. Are you the lab tech?
What does that mean?
That means you're the technical assistant for all the laboratory progress.
I'm an employee.
An employee, yes. Okay, you're an employee.
Ooh.
Wait.
It's not reactive.
Look, look.
No, we're not.
Okay, but we need, all right. I know, wait, okay, but I do need to teach properly. So, so next time I have money, you get $7.
Yes. And I'm here too for 2 hours.
Really? Okay. Well, let's get started. All right. This is what we always.
Can I
hello. What?
Anywhere.
Yeah, you can sit there. Hi, Kazi. Hello, Elena. Hello, Anna. Oh, Anna said hello to you. I mean, Anna said hello to you.
Hey, yo, my name
and-
is Felix, and I'm gonna go grab myself a chair. Daddy,
Oh,
you
okay.
get a chair. I don't want to grab
Well-
myself a chair.
Well, I do have to teach though. This, and yes, that is my son. This is my. It says, "Is that
Fine.
your son?" Kazi says, and she says, "Hi," and hello, Shasha. Hello, Alex. Hello, Marlon. Hey, Asmita. Hello, Shasha. Hello, Grisella. Hi, Noreen. I'm still not saying it right. Noreen. Hello, Diana. Hi, Hannah. And wait, no, I'm saying that wrong also now. It's been so long since I've seen you guys. Oh, no, yes, it is Hannah. Yeah.
Yeah, you said it right.
Oh, is it? Okay, thank you. Okay, thank you. And hello, Kwan. Hey, Adriana. Hello, hi, Kareem. No, sorry, Noreen. Oh, I did say it right. Okay, okay. And hi, Cassandra. Oh, and my son is back. Okay, but just forgive this for this will happen for a few minutes.
Help me,
Hello,
Daddy.
oh my God. Oh my God. Wait, okay, wait.
I carried this all the way from the laundry room.
This was in the laundry room?
Yeah. Like, there's like 2 and I can't remember.
Okay.
Can I see 2?
Yes. You see.
Can you zoom in?
Yes, hold on.
Hi, my name is Felix.
That is true.
Can you not be on the screen?
What? Okay, but I do, this is actually a job that does have to get done. But, they're asking, what are you teaching? Someone wrote, hi, Felix, what are you teaching us today? What's the, oh, math. Okay, math, do math.
Okay, you go first, Daddy.
We definitely need that. We definitely need math in this class.
That's
Dad,
funny.
you go first. Daddy, you go first while I think.
Okay, here's a math question. How many Pokemon do you get in your party?
What? How many? Daddy, that's not a math question. They don't know about Pokemon.
Oh, they don't? None of them know about Pokemon? All
Maybe
right.
some of them, but we want everyone to know about the subject. I want everyone to know about Pokemon.
Okay.
Daddy, you have to do things that everyone knows.
Okay. Okay.
Like
here's
a
a-
simple, let's start off
Oh, here's a good
simple.
math question. If it's if there's 2 hours in a class, how many minutes is that?
Yes.
You tell.
No, I want them to guess. What
Okay.
your guesses, everyone? What's your guesses? How many minutes is 2 hours? We know the answer.
Do you know the answer?
Yes.
Well, oh, nice. Whoa, nice.
No one heard that.
Great. Okay. Wait. Okay. This is my oh, they're saying
What's it
oh,
say?
this, oh my God, someone put in a picture. I'm worried what's gonna be in this picture. I don't know if it's appropriate for our
Wait, what does this say?
that says it says Felix is cute, actually. That is what it
I
says.
am not cute. I am the strongest 7-year-old in the planet. Fine, I might be cute, but I'm definitely the strongest 7-year-old in the planet.
Okay, there we go. All right, and they wrote that mean. Do you know what? Remember what LOL means?
What?
L-
Laugh.
Yes.
What did they say?
Laugh out loud.
Loud.
Right.
What's the picture, Dad? We haven't
What picture?
seen that
What picture?
picture that you saw.
Professor, I sent the image of the question 4. I watched the video, but I have a question. Why can't we use that formula that I used in my homework for question 4 from my previous notes from the previous semester? If you could address that at the end of the class, after the class, so we don't take,
Oh, no, that's a great question.
What
I
are you
will
talking
Wait,
about?
so she's actually talking about the physics that we do need to start talking about in this class. She's actually talking about the actual.
Can we
she's talking
do
about the-
math next?
Right, but we do have to do the math that's actually part of this class. And that is a very good question. And I may,
After that math.
wait, okay, but we actually do have to get rolling here. Hold on. So
After that
all right,
math.
do one. All right, so one math question, but no, okay, Yulia, yes, good point. And I'm going to try to address it during class. I think it's actually relevant. I'll have to look at that in a
Can
second.
I ask the
But-
math
Okay,
question?
ask one math question.
Okay,
And then.
good. Okay. What is 20 plus 20? Everyone,
40.
in chat.
Oh, did you hear it? She just
What?
said, she just
What?
said,
40.
oh, do you agree?
Yay.
All right, good deal, good deal. All right, so good deal.
Moving
So-
on.
Okay, let me move on to actually teach them what we have to, so that, and then I can come and play as soon as this is over,
Okay.
okay? Okay.
I'll be sitting.
Oh, and they even put 40 in it. Oh, someone put 200, that's funny. Oh, look how many people, oh my God. Look
Whoever
how many
gets
people,
two,
look how many people answered your question. 1, 2, 3, 4.
whoever gets 200, I'm sorry, but you are
Oh,
wrong.
okay, I think Kazi is being nice. All right, all right. Okay, now I really have to teach.
I
for
don't know
seriously.
if that's a mistake or not.
I think. Okay, I want to see what Yulia put in there here. Hold on one second. I just want to see this.
Ooh, iPad.
But, okay, but now, okay, but for real,
Okay.
I do have to teach that for real. I need that. Because watch.
Okay. Done.
That's the class. Okay.
But it,
So,
can I
oh,
see?
hold on, wait, please stop.
Poopy pants. What does that
I'm
say?
sorry, right now, I'm looking at the thing that Yulia just, I am trying to get rolling here. I apologize, but I'm looking at what Yulia put in. Oh. Okay, no, I'm definitely going to address this with everybody. This is very, very helpful. And you also get points for submitting an image. This is great. All right, and I'm gonna, yes, okay, and then I have to.
When I come back.
Yeah, I just figure it will be. I just send you the formula that I used in my question 4, but I know you already addressed it in your video that whatever that it's not correct. I'm just wondering why, because it has a V initial and V final, as well as it has a mass and it has a total of forces and delta X in there as well. So
Oh yeah, you are right. No, I definitely, I think this is a good place to start. I mean, for us to start the class. One thing you say that, and I'm glad you saw the video. I was going to ask, I mean, I did want to get to that, but you're saying that in my video, I said this is wrong?
no. You just said that some of the formulas that we already know from physics 1, they are not applicable for the specific problem. So this is one of the formulas that I found in my notes when I was doing the homework, and I was thinking if I could actually use it or not, because I saw you didn't get to the answer for that specific problem. So I was wondering if it's okay to, and why would it be wrong if it's not okay to use that formula?
Oh, okay. No, great question, great question. And you're absolutely right that I didn't get to the answer yet in the video. And that's one of the first things I want to do today in class. But let me also be clear, try to be clear. No, this equation is the kind of equation that we need to use for question 4. When I was saying, okay, I'll start writing in the pad in a second. When I was saying you can't use certain equations from physics 1, okay, I see in the chat. Good, thank you. No, what I'm saying is you can't use like x equals 1/2 at squared plus v naught t, or x equals v squared minus v naught squared over 2a, or like you can't use the same equations that you used for questions 1, 2, and 3. And I'll be more specific. I'll start writing on a pad in a second. What I'm actually trying to say, to tell you the truth, I'm trying to say that you are right that for question 4, oh, and I keep forgetting not everybody else is looking at your image. I'll screen share it in a second. I'm just getting myself together here, but no, I'm trying to say that for question 4, what we need to use is something like what you were doing, something with 1/2 mv squared and something with work and kinetic energy that forces and acceleration won't work because the accelerations and the force is not constant. So we have to do something with work and energy like what you are doing. Like what you're doing is actually the right thing. That now I will admit that I'm not sure I agree with the answer. I mean, I think there is a slight error in what you're doing that.
Yes, because when I was calculating for the F net, I think I got confused a little bit. So I was wondering, that's why I was waiting for the grades to come back, but I figured we'll go over it today before my grades come back so I could actually see whether it's right or wrong.
Right. Okay. So you're right on all counts. I appreciate that. Yes. So, and again, I know so everybody in the class, I know you don't know exactly what, because I didn't share the screen that she's talking about. So I know not everybody knows what we're saying, but so let me back up for a second. Yes. What's going to happen is in a minute or two, we're going to keep going over homework 1. We're going to pick up from where I left off in the video that I asked everybody to watch. It is true what Yulia is saying, that I'm going to give more solutions and answers and whatever to homework 1, which means that, and yes, it's true, I haven't given the grades back yet. I'm totally falling behind and I apologize. But it does mean that if I give information today that helps anybody, or anybody thinks anything they did in the homework was wrong, or they want to update it or improve it, they still can do that. All of you can still do that, whether you get the grades or not. You are allowed to do whatever you want at any time to keep bringing all the way up to the full 20 points or whatever number of points it's worth. And so that's what we're going to go over today. And I'm going to get the pad out in a second. Well, yeah, okay. I'm not sure if Yulia wants me to. I might. So I'm going to go to the pad. I mean, I'm going to start drawing on the whiteboard, picking up for the homework. I might, well, Yulia, she shared an image that I guess everybody can see on their side. And she definitely, just for the record, also, remember, she totally gets points for putting an image of any kind, like a screenshot of her own notes, into the chat. She gets points for that, no matter what was in the, I mean, even if the image, even if it had an error, she would get points for that. Whether I share with everybody or not, she gets points. I probably will share with everybody to make a point about it, but anybody can see it anyway because she put it in there. What was that? It was one other thing. And yes, I know I took a long time to post the video. Oh, there it is again. Okay, great. Awesome, thank you. Oh, because it was in direct chat before. I'm sorry, is that? Oh, it was direct. I'm sorry. Okay, so now she totally gets point. Okay, that's awesome. Thank you. Also, I just want to say, I know, so that video that you were supposed to watch that substituted for the 75 minutes from last week, I know it took me a while to post it. I know it's maybe still possible that some people maybe still haven't seen it. I do need you to watch it so that all these classes eventually make sense. Like in other words, I'm not going to backtrack today, and I'm not going to go back over the same things I was saying in the video. I do expect that people either saw it or shortly will see it, but I will, what I'm going to do right now, just so that we're making sense, so that we're on the same page, and so people follow what Yulia is talking about, because it is totally relevant, is like she's referring to things in the video and they are making sense to me, what she's saying. What I'm going to do now, though, in a sort of a strange way, just so that we can all get on the same page, I'm going to on the pad, on the whiteboard, I'm going to actually do out question 4, because I think that's what we're up to. Yeah, like, I'm sorry. I talked a lot in the video, building up all these concepts that are relevant to question 4. I talked a lot about how like certain ways you can't do question 4, blah, 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 blah. And it got very mathy, and maybe it did lose some people, or I don't know. What I'm going to do right now is I'm just going to, right now on the pad, I'm going to write out what I think is the correct way to do question 4. I'm just going to write it out so you can see, and you can see the correct answer. In fact, I'm going to do question 4 and question 5 right now. I'm just going to write them out so you can all see. And again, you can use this to revise your homework or to hand it in or whatever, or improve the grades, or check your homework. I'm going to write it out. Then I'll start trying to talk about it and answer questions and relate it to what Yuli is saying. But again, just so that we're all clear. And so hopefully what I'm about to write out on the pad will kind of hopefully will help all of you, whether you fully absorbed the video or not. I'm trying to say that the video kind of justifies what I'm about to write, but right now I'm just going to write the solution. I mean, so especially if you remember anything from Physics 1, this might make sense to you. If you don't, and you didn't see the video, you'll tell me what you want to ask questions about, and you can compare it to it's very similar to what Yulia just put in the chat, very similar, but I just to warn you, I will get a slightly different answer from hers, because I think there is one slight maybe mistake in what she's doing, or like just a math kind of computation error. But anyway, so I'm going to shut up for a second. I'm just going to write out the solution to question 4. And you guys copy it and see where you have questions or what. Okay, if that makes sense. Okay, I'm going to go to the next page in 1 second, but just notice. So I'm just, again, because it's been a couple of weeks since we've seen each other and blah, blah, blah. And of course, I'm trying to explain this problem or this solution in this physics, but I'm also trying to remind you or re-explain to you how I think physics problems should be solved in general, like the general 5-step procedure for turning in homework problems, exam problems, research situations, etc. So just to remind you again, sorry to belabor this, like, so notice I have the diagram and the fact pattern first, DFP, step number 1. I have the diagram and the basic givens or fact pattern, like presented as number 1, right? Then number 2, WIQ, what is the question? Like, these are like the little comments that I can't do or make on homework and whatever, and on exams. So I have the question next. The question is at, oh, I'm sorry, excuse me. That is right, but that's the wrong question. The question is, I'm sorry, the question is at x equals 0, I'm sorry. The question is at equilibrium, what is the instantaneous speed of the mass, right? So that's the question, WIQ, what is the question, step 2. Then step 3, notice, and this is a part that people take a little while to get in this habit, instead of just diving in and starting to plug in numbers or crunch numbers or do algebra, I always start with a general definition or principle first. I start with something that's, it might be in English, it might be an equation, but it's probably not numbers. And it's not just specific to this problem, something that is a true principle or a law or a definition, something that is true in general, that then I'm going to soon apply, particularly to this problem. So my general true principle here, step number 3, is energy is conserved, right? Like in English, I'm saying energy is conserved, and in a way that's what I was spending a while starting to talk about in the prior video. But how do I write it? I mean, as an equation, I say capital E sub A equals capital E sub B. And again, you're going to see, if you looked at Yulia's screenshot, I mean, in a step or two, you're going to see how that's what she's doing too. But by capital E, I mean, in fact, I should say, like, capital E stands for total mechanical energy. And by A and B, I mean particular places. A and B are places, like X equals A is some spot, X equals B is some other spot. Again, this is a general principle. So A and B would be any 2 places, but specifically they would generally be, A would be a spot that you know something about, specifically a spot that you know, for which you know the speed at that spot. And then X equals B is the other spot, the spot that you're solving for, the spot that you don't know the speed. Okay, that's a general principle of energy conservation, is the total energy over at one place is the same as the total energy at any other place, right? So now I go to the next page. I'm still writing down general principles here. Sure. Okay. Okay, so I'm just defining, so in this particular case, right, by X equals A, the known spot, I mean X equals 0.15 meters, because I know there the speed is 0 there. And then the other spot, the spot that I'm solving for, is the spot of X equals 0, where I'm looking for the speed, right? So I'm just defining it. So now I'm continuing to expand. Now, what do I mean by total mechanical energy? Oh, sorry. Oh, no problem. Got it. No problem. Thank you. Oh, did I even say hello to everybody? I'm sorry. Oh, yeah, I did. Okay. And so did Felix. Thank you for indulging, Felix, by the way. I know that was a little bit disruptive. Welcome to my world. Okay, but thank you for your kind feedback about that. All right, so now what do I mean by total mechanical energy? I'm still in general definition land here. Like, I haven't said anything particular about this problem. Whatever I'm writing right now is like true in general. By this, I mean the total amount of kinetic energy plus the total amount of potential energy. This is where we're about to get into the realm again that like Yulia was remembering from a prior class. And this is, I'm not saying this is wrong, this is right. There were certain equations I was saying in the video, I was saying there are certain equations for problem 4 that you cannot use, that won't work here. Certain equations from early physics. I didn't mean all equations from early physics are off base. I mean, or off limits. I mean specifically the kinematics equations, like the constant acceleration equations, like x equals 1 FAT squared plus V naught T. That stuff won't work. Or even F net equals MA, the things that we were using for questions 1, 2, and 3, they won't work here because the force is not constant, the acceleration is not constant. But total mechanical energy is defined to be all of the kinetic plus all the potential energy at one spot has to be equal to all of the kinetic energy plus all the potential energy at another spot. Oh, by the way, why is this the case? Like, and again, this is sort of what I was trying to get at in the posted video, but the reason I am allowed to believe that all the energy is conserved, and the reason that I'm allowed to use this equation, or the reason that I would even think to want to use it is this. Yeah, whoops, sorry. This almost sounds like circular reasoning. It almost sounds like redundant, but yeah, I'm just saying a general principle here. The principle is if all the forces doing work on a system are conservative, then total mechanical energy is conserved. Now that almost sounds like, well, duh. I mean, if the forces are conservative, the energy is conserved. What does that actually mean though? Let me back up and say a sentence. Again, sort of based on the video that I did. Oh, sorry, Yulia, yeah.
I was gonna ask, you're basically saying that the energy is not like created nor destroyed, it just transforms from one form of energy to the other. Is that what you're trying to say? Or that's a little bit different?
No, that's a really good question. That is what I'm trying to say. If we both mean, okay, well, and I'm gonna write what I'm trying to say. What I'm specifically trying to say here is that any kinetic energy that seems to be lost in the system is not actually being lost, or is being stored for later, or any energy that's being lost from one place in the system is being stored for another place. Now that is very similar to what you just said, like that energy is not being created or destroyed. Let me say to everybody though, the slight difference, like she's definitely right. There's no question that in the whole universe, energy is neither created nor destroyed. It is just moved around from place to place, and it's just converted from one form to another. But now that's a very broad statement. Like, for example, that means in the universe, for example, I could take one hand, rub it against another hand. So I've got this hand sliding, it's moving. It's got all this kinetic energy, then it hits my lower hand, and my lower hand starts slowing down my upper hand. So my upper hand seems to lose some kinetic energy. Now, what Yulia is saying, that's right, and this is a slightly broader point, that even though my top hand seems to be losing some kinetic energy, i.e. being slowed down by my lower hand, in the universe, that energy isn't just disappearing. Energy can't disappear, it can't be destroyed, and just like it can't be spontaneously created. What's happening in the universe right now? Well, the kinetic energy of my top hand is being converted into a different form of energy called thermal energy, i.e. heat, i.e. the kinetic energy of this hand is being dissipated outside of this system, and the top hand is being slowed down by the friction of the lower hand, and creating heat that dissipates and then heats up my two hands. So that's why I do this, to heat up my hands. Now that is an example. Energy not being created or destroyed anywhere in the universe, just moving from a system outward it's moving from one location to another, moving from my hand outwards around my hands, and from one form, kinetic, to another form, thermal. That is true. That is what Yulia is saying, and it is true. However, what I'm saying here is something even more specific. Here I'm saying mechanical energy itself is not even being lost or gained in this system. Like I'm saying, we're not even losing any kinetic energy to the form of heat or anything like that. We're not even just conserving the energy in the universe. We're actually conserving all the energy of motion in this mass that's on the spring. Like it's not even going to lose any of its energy and then start heating up the table or something like that. It's actually going to retain all of its kinetic energy, even when it seems like it's slowing down. Even when it seems like it's slowing down and losing kinetic energy, we believe it's storing it in the form of potential energy for a little bit later when it's going to start speeding up again. Like that's, so what I'm saying, so this is like a very specific version of what Yulia is saying. In broad terms, what Yulia is saying is, in general, energy is not created or destroyed in the universe. And then I'm saying here, yes, even specifically, mechanical form of energy, energy of motion, is being retained in this system without even being turned into heat or affecting any other system or anything like that. So this is what I mean. Okay, so I'm giving a definition here. This I'm picking up again now from where I was in the video. In the video that most of you watched for today, and some of you still might watch, and please do if you haven't watched it yet. Like I was talking a lot about the definition of work. That work is a force acting through a displacement, and if you do a little bit of, if you exert a little force over a little bit of displacement, that's a little bit of work. But then even if you exert a force through a big displacement, even if your force is changing continuously, you add up all the little bits of work that you do, and that gives you the total amount of work that you do throughout the big displacement. In short, what I was trying to say in the video, or at least a big part of it I was trying to say, is work is force through a displacement right now. And again, a lot of you already know that. Okay. Now I'm saying, if we have a kind of force where we know for a fact that over any round trip it's going to do zero work, then we call that force conservative. And there's three main examples of such forces. I'm going to write them down here on the next page. Quick explanation of this distinction, very important distinction. And remember, work is force times displacement. We actually do it. Yeah. Work is force times displacement. Remember, force is a vector, displacement is a vector, i.e., and you might want to write this down. I'm worried about getting myself too bogged down or too off the topic or getting these notes too confused, but you may want to write what I'm saying right now down. Remember, force is a vector. Direction matters. Displacement is a vector. Direction matters. What I'm really trying to say here that somehow or another, maybe put in your notes, I'm saying when it comes to force and displacement, and therefore when it comes to work, negative signs and positive signs really, really matter. Even more specifically, if I push something in the same direction that it's displacing, right? Work is force through displacement, right? And direction matters. So just remember, I mean, I think many of you have heard this before in Physics 101 or whatever, but don't, and again, maybe this is like background to question 4, and I really do want to solve question 4 and get an answer and discuss Julia's thing. I don't, forgive me, but work is force times displacement, and positives and negatives matter. So if I exert, so say we call up positive and we call down negative, like we don't have to, but let's just, but we have to call we call one direction positive and we call one direction negative, right? Let's say the up direction is known as positive and the down direction is known as negative. Okay, that means then if something's going up while I push it up, if I push positive or pull, if the force is positive and the displacement is positive, then positive times a positive equals a positive. That would be positive work. And I would be giving energy to the object, right? Similarly, if I'm pushing something down or pulling something down while an object goes down, then it'd be negative times a negative, and that still yields a positive, right? So whether I'm going down or going up doesn't matter, but as long as the direction of the force agrees with the direction of displacement, if you have a positive times a positive or a negative times a negative, then you have positive work, right? So if the force and the displacement are aligned, are in agreement, then you're doing positive work. And what that ultimately means is you're giving kinetic energy to an object, okay, right? So if I push something down with my hand, if I push it down and it goes down, oh, right. Oh my God, great question. Oh, Quan, thank you. But Quan, great. Yes, you're totally with me. Right. If they have opposite signs, that's so great. That so shows paying attention. I'm sorry, I shouldn't be so excited, but I am. Yeah, if the force and the displacement have opposite signs, if they disagree, then you have a positive times a negative or a negative times a positive, either one, and you get a negative. So what does that mean? That means you're doing negative work on a system and you're thereby taking energy away. Now, this actually makes sense in the end, hopefully, if you see, like if I push something that, again, positive could be any particular direction you like. It could be up, it could be right, it could be north, whatever you're saying. But if you're pushing something and it's going that way, that means you're doing positive work. You're giving energy to the system, to the object, and therefore, if you're doing net positive work on the object will gain kinetic energy and speed up. If you're pushing against something while it goes the other way, and I'll give you an example of that in a minute, it's totally conceivable that can happen. For 1,000 reasons that can happen. If I'm, so for example, if a football is coming like toward me, right, and I stick out my hands to catch the football, right, so the football's coming this way. Now I start pushing on the football. I start pushing the football that way in order to catch it, right? At least for the first few milliseconds or first few instances, the football's going this way, but I'm pushing that way. So what's happening? I'm doing negative work on the football. I'm slowing it down. That's what I'm trying to do. I'm doing negative work. Like negative work doesn't have to be a failure or an accident. It simply means I'm taking energy away from the football, which means I'm slowing it down, which in fact is precisely what I'm trying to do when I catch a football, right? Or catch a basketball or whatever. So if the force and the displacement, and so please do, I'm so glad Kwan just asked that. And again, this will come back to Yulia's question. This will come back to question 4, and whether this is review or clarification or whatever, right now, what I'm just trying to say is if the force and the displacement are aligned, then we're doing positive work. We're giving energy to a system. If the force and the displacement are in contradiction, are in disagreement, then you have a positive times a negative, then you're doing negative work on the system. And that's not bad. That just means you're taking energy away from the system, slowing it down. One quick step further, let me say, remember Newton's third law. If I push you, you necessarily push me in the opposite direction, right? So in other words, when I catch the football, or anytime, like if I push against something, I'm taking energy away from the football because the football's coming in, but I'm pushing like that. But by Newton's third law, the football is coming in and it's pushing my hands a little bit that way, right? So I'm doing negative energy on the football. The football is doing positive work. I'm sorry, I'm doing negative work on the football. I'm taking energy away from the football. The football, by Newton's third law, must be doing positive work on me. It's giving me energy, whatever energy. And this goes back to Yulia's thing. This is how energy is neither created nor destroyed. If I'm taking energy away from something, where does it go? It goes to me. If I'm doing negative work on you, you're doing positive work on me. If I'm taking, then I'm getting. If I'm taking, then you're giving, if that makes sense. Now, how does this relate to conservative and conservation and all that? Now let's look at this carefully a minute. I mean, it's like this is a really simple idea, but it's a very profound idea. And it's just like one of those many ideas in physics. It makes sense, hopefully, once we think about it, but we might not have thought about it until we thought about it. So what I'm getting at is this. Say I throw something up and it comes right. I throw something up and it comes down. So I throw it up. It's going. It reaches a peak height and then it's coming down. It's going down. I just threw this pen up in the air. Okay, let's just examine its trajectory while it's going up. While it's going up, the object is moving up. It's moving in a positive direction, but gravity is pulling down on it. The displacement is positive. The force is negative. So gravity, planet Earth, is doing negative work on an object while the object is going up. Now, again, that's not a contradiction. That's not a failure. It's not a problem. Like the object is going up because I gave it an initial velocity because I threw it, right? But then my hand is no longer touching it. So now from that initial velocity, the object, I mean, it takes a while for it to lose its velocity. So it's moving up, but the force of gravity is pulling down on it, right? So the force is down, the displacement is up. So what does that mean? That means gravity is doing negative work on the object as it goes up. It's doing negative work. That's not a problem. It means it's taking energy away from the object, the object is slowing down, just as we would expect. No contradiction, no problem. Let's be more specific, in fact. And again, you might really want to write this down. I'm afraid if I start writing, I'm never going to get back to the topic. But if you remember that work is force times displacement, let's say we throw something up to a height h, right? Then while it's going up, displacing height h, the force on it is down negative mg, right? So the force is negative mg. I'm just saying negative because if we're calling down negative, we're calling up positive. So the force is negative mg. The displacement is positive h. So while the object is going up, and please do write this down if you can, please do. While the object is going up, gravity is doing work negative mgh on the object, right? While it goes up, and this goes to Kwan's question, gravity, planet Earth, is doing work negative mgh. The object is losing energy. How much? Negative mgh joules it's losing. Then the object gets all the way to the top. Now it starts falling down. Now the object, my pen, whatever. Now my object is going down. It's displacing in the downward direction. So you could argue its displacement is negative h now, like it's going to go back that same distance, but downward. So it's negative now. But the force on it is still negative. Gravity is still pulling down. Gravity was always pulling down. So now the force is negative mg, but the displacement is negative h. So you multiply those two together and you get that the work that gravity is doing on the object on the way down is a negative times a negative that makes a positive. The work that gravity is doing while the object is moving down, gravity is doing positive work on the object, positive mgh. That might sound a little strange, but again, that's not a contradiction. We're saying gravity is doing positive work because the force and the displacement are in agreement with each other. Gravity is giving energy to the object. It's gaining energy. Well, duh, it's speeding up. And how much energy is it gaining by? How much of an amount is it speeding up? Positive mgh, right? So I'm not saying that this is hard or complicated. I'm saying do track this, do pay attention, because we're about to make a contrast to it. So I'm saying if you just throw something up and let it come back down to its original height, if you send something on a round trip, a closed path under the influence of gravity, if it goes up h, comes down h back to the same original spot, the total amount of work that gravity will do on that object is negative mgh plus positive mgh. That makes 0, right? Now, again, I hope you wrote that down, but hold that thought for a second. It may seem totally obvious. I don't know. It might seem totally obvious to some of you. It might be like, yeah. What's the point? Duh. But here's the point. Not all forces do that. Gravity does that. If we run the numbers, we'll see that the springs do the same kind of thing. On your way out, they do negative work. On your way back, they do positive work. For the whole round trip, the positive and negative add up to each other and you get net work 0. But look, that's actually an interesting thing. It's even if it's simple and you can follow it, it's actually interesting because take a normal everyday force like friction, right? Friction does not do that. If I send this object along, if I call now, the direction north, if I call that positive and I call the direction south back to me negative, if I throw my pen on the table and let it go out, or I pull it along the table and I let it go a distance X, I watch it as it's going out and I look at the amount of work that friction, the force of friction from the table is doing on it. Like while the object is moving north, a displacement X, friction shoves the other way on the object because it's friction, right? It rubs against the velocity of the object. So while the object is going out a positive displacement X, force of friction, call it F, is pushing back on the object, negative X. So on the way out, displacement is one way, friction is the other way. This is Kwan's question. They disagree with each other. They have different signs. So it's a positive times a negative. So on the way out, friction does negative work. Of course, it takes energy away from the object. The object slows down due to friction, right? Now, if I start bringing the object back in for whatever reason, however, like either with my hand or I tilt the table or what, if I impose some other force or if I just flick it so it comes back the other way, I don't care what the cause is. It if I look again at how much work friction is doing, like there could be many forces involved in the problem, but if I'm focusing all my attention on one force at a time, so I'm looking at friction here, as the object comes back, that negative displacement, negative x right now, so if it completes a round trip by whatever mechanism, on its way back, it does displacement negative x. The thing is, on its way back, friction is going to flip, right? When the object is moving to the south, friction is now going to point in the opposite way and push north, because friction always points against the motion of an object, right? In other words, friction is not like gravity. Gravity always pulls objects down towards the ground. Gravity is always pulling toward a particular place. There's like an equilibrium place associated with gravity that we call the ground. Gravity wants everything to be on the ground. If you're moving up, gravity pulls you down. If you're moving down, gravity still pulls you down. Friction doesn't do that. Friction's not trying to get you to any particular place. There's no equilibrium spot associated with friction. Friction just says, if you're moving north, I push you south. If you're moving south, I push you north. Friction just resists your velocity. That's a completely different kind of force, right? I mean, it's just as simple. I'm not saying it's hard, but it is different. Friction always points opposite to your motion. Gravity always points down. Totally different. One last way to put it is that gravity has an equilibrium spot associated with it. Friction does not. So mathematically, on your way out, friction's doing negative work, right? Because your displacement's positive, your force is negative, so on the and multiply together, you get a negative. So on your way out, friction's doing negative work on you. Then when you come back in, now granted, if you're coming back in, probably something else is pulling on you or helping you, but we're not looking at that. We're looking at the friction. On the way back in, you're doing now negative x displacement, but now the friction's pointing the other way, so friction's positive f the other way. So on the way back in, you still had, like before, on the way out, you had a positive times a negative. Now on the way back in, you have negative times a positive. It's still negative. In other words, whether you go out or you come back in, either way, both ways, friction does negative work on you the entire time. So if it did negative work on you of negative F times X on the way out, say negative 2 joules on the way out, then on the way back in, it does negative 2 more joules. The total amount of work that friction does on you for the entire round trip would be like negative 4 joules. You could look at another 4, right? So friction's like always doing negative work no matter what. You could look at a different kind of force, like the normal force, or like pushing what's happening with your hand, pushing the pen, helping it go out. If you want to look at that, the normal force, it's the same logic, only it's positive now. When you push the pen out, you're pushing out, the pen's moving out. So you're giving energy, you're doing positive work. Say it's 2 joules on the way out. Then if you turn your hand around and bring the pen back in toward you, well, then again, you're bringing the pen in and the pen is displacing in. So on the way out, you might do your normal force of your hand might do positive 2 joules of work, speeding up the pen the whole time. On the way back in, your hand does another positive 2 joules of work. So you do a total of like positive 4 joules for the whole round trip. I'm not saying that's complicated. I'm not saying it's supposed to be a trick or something, but I am saying that is a total contrast to what gravity or springs or what we're going to find in this course or the electrostatic force do. Though these forces here all have some sort of equilibrium position or orientation or configuration associated with them. Gravity always wants you to be on the ground. The spring always wants you to be in the center of the spring. Electrostatic forces like always want electrons to be near protons. They are conservative. Oh, and there's something in the chat. I'm sorry. It might have been there for 50. I'll go to the chat in 1 second. I'm sorry. But what I'm ultimately saying, and I will get back to the problem, I promise. But conservative forces like gravity, elasticity, electrostatic, what it means to do well, in fact, let me write this. I will get to the chat, I promise. Let me just write this before I forget. Okay. I'm about to get to the chat. I know I said that I just wrote this very illegibly. Let me just read out loud what I just wrote and say the point, and then I'll get to the chat. I'm just saying, if a conservative force is one that we know will do zero work over any round trip, any closed path, right? Like gravity, like it does positive work on the way out, then it does negative on the way back, or the other way around. It does negative on the way out, positive on the way back. Then what we can say about any conservative force is anytime it looks like the conservative force is taking kinetic energy away from something, anytime it looks like the conservative force is doing negative work, taking away kinetic energy, we can actually say that the conservative force is just conserving, storing that energy for later, storing it to give back on the return trip. If you're losing energy on the outward trip under the influence of a conservative force, since we know in advance that you're going to get it all back on the return trip, because we know the total amount of energy loss or gain, the total amount of work for the round trip equals zero, then whenever we see a dip in kinetic energy, we can just say, oh, it's not really being lost. Like, we don't even have to say, in other words, oh, it's being turned into heat, or oh, it's going into this other part of the universe, or oh, it's going into this other system. If a system is being worked on by only conservative forces, whenever the system is slowing down or seeming to lose kinetic energy, we can say, aha, no, don't worry about it. It's just on its outward bound trip. Like, it's looking like it's losing energy in that traveling that it's doing right now. But actually, if we were to keep on waiting and keep on watching and let it come back the other way, it would get that energy back. So whenever it's looking like it's losing energy, we can just say it's storing energy as potential. Potential energy is whatever work would be done by the conservative force to bring the object back to equilibrium. In fact, I'm going to write that, and then I promise I'm going to get the chat. I just don't. I want to get this thought out before I. Okay, let me just look. So now I'm going to relate this back to the equations of question 4. I know I'm getting sort of abstract here. I'm going to come back to question 4 and relate this to the equations, to the problem solving. Let me just see what it is in the chat that I missed. Sorry. Oh, it was what Quan said, which was a great question. Okay, so I did okay, that was great. And well, okay, so sorry about that. So let me relate now back to Okay, so so potential energy in general is the work that some conservative force would do to bring an object back to equilibrium. Like the work that gravity would do to bring something back to equilibrium would be mgh, right? Force times displacement, force of mg times displacement h. The work that a spring, I mean, the potential energy due to a spring would be that the work that a spring would do in order to bring something back to equilibrium, that's 1f(kx) squared. So okay, so now I'm starting to do the thing that in effect Julia was doing in her screenshot in her homework. What I'm saying here is, let me slow down a little bit. What I'm saying here is, okay, as long as all the forces doing work on a system are conservative, then what we're saying is anytime it seems like you're having a loss in kinetic energy, you're really just storing it as potential energy. Anything that you're going to lose on the way out, you're going to gain back on the way in. So any two spots in the whole journey will have the same total amount of energy, as long as by total, we mean all of your kinetic plus all of your stored potential. Like that should all of your kinetic plus all of your potential should be the total amount of energy that you would ever have in the system. And that's never going to change. It's never going to go up or down, because the total, because work is the transfer of energy, and over the whole round trip, zero amount of work evidently is being done. So I'm saying the total amount of kinetic plus potential over here must equal the total amount of kinetic plus potential over there. I'm saying kinetic energy is 1/2 mv squared. Potential energy is 1/2 kx squared. Those two things, by the way, I may not have explained those in the video, and I'm perfectly happy in a couple minutes. If anybody wants to stop me, I can go back and explain in depth. I can explain in depth where I got the 1/2 mv squared and 1/2 kx squared from. I'm sort of thinking that you know it from physics 1, but it is occurring to me that I didn't actually explicitly say them in the video. So I'm happy to re-explain those or explain those for the first time. But for the moment, just bear with me. I'm saying kinetic energy is always 1/2 mv squared. Potential energy for a spring is 1/2 kx squared. Therefore, the 1/2 mv squared plus the 1/2 kx squared over here at spot A has to equal the 1/2 mv squared plus the 1/2 kx squared over there at spot B. Remember, spot A is the initial position, 15 centimeters. of stretch. The spot B is the equilibrium position that we're looking at, spot B. X equals 0. So now I'm going to solve in a minute, but first I'm filling in some things that are easy to fill in. Like if I look at spot A at X equals A, the initial place, 15 centimeters from equilibrium. Well, the problem told us that there was no speed there. That's when the mass was released from rest from that spot. So V at X equals 0.15 was 0, right? So I'm crossing that out. I'm saying it turns out there is no kinetic energy at the very first spot of this whole thing. I'm not saying that's always true. I'm not saying that whenever anything's at 15 centimeters, it has no energy. I'm just saying in this problem, we held the spring out initially at 15 centimeters. And we know for a fact that we were holding it there with a speed of 0. In fact, that's why I'm using the 15 centimeter spot as one of my 2 spots of comparison, because I know the speed there. And it happens to be the nice easy number of 0. So I cross out the V at spot A, I call it 0, I cross it out, and 0 times anything is 0. So that whole term is going to go away. Then I go over and look at spot B. Spot B is X equals 0, the equilibrium spot. So the X is 0. So I'm crossing that out for spot B, right? Again, stop me if there's so continue the next page. I'm just going to recopy just so you can see, but right. So those terms are across. So continuing on then. So I have and I can divide both sides by 1/2. I could have done that right away if I wanted to, but whatever. So now kx squared equals mv. Now notice this. No, I'm continuing. I'm solving the problem. I'm almost at an answer. Notice that I'm doing as much algebra and as much as I can before plugging in any numbers, right? I haven't plugged in any numbers yet. I'm looking at what is true. So, and what am I solving for? I'm solving for V, right? So before I plug in any numbers, I'm going to do a little algebra and get V by itself. I'm going to isolate V. I mean, some of you like plugging in numbers right away. I'm trying to get you in the habit. Try it a different way. In physics, try to postpone the numbers as long as possible. Just try to get in that habit. So I'm rearranging and saying, so in other words, but now I plug in the numbers. And all of this work that I'm doing right here, by the way, all this work where I take the general principles and I'm now applying them to the particular problem, right? This is step 4 of the problem solving of the 5-step process. I call it PAW, particular application and work, right? And again, just for the record, this is a step that generally a lot of times people skip straight to when they're solving something that they kind of think they know how to solve. But then if they get to something that they don't know how to solve, they don't know what to do because they've always been skipping to this step. And the way to solve a problem is first do the first 3 steps. And you can always do those steps even if you don't think you know what to do. Anyway, so this is step 4, particular application and work. Okay, so but now I'm which really kind of means rearranging and plugging in the numbers. Okay. And if I plug in the numbers, we're going to find Like that's the answer to question 4. Now, and I want to move on to question 5. I mean, I know I want to sort of catch up. I want to move on to question 5. I also want to say for a minute, again, because I'm so glad that Yulia started us off today. It actually kind of helped. It helped ground me. It also helped get my son out of the room, I guess. Anyway, whatever. So I want to say, if you look at her screenshot that she put in the chat, she is doing the right thing. What is right about what she's doing is she's using work and kinetic energy. She's using energy arguments to solve this, which is the right thing to do. You'll see in her screenshot that she has a 1/2 mv squared minus 1/2 mv squared going on there. And that is right. What I was saying that cannot be done for this problem is just things like F net equals ma or x equals 1/2 at squared or something like that. Because again, the force and the acceleration were changing continuously. And whenever you have a changing force and therefore a changing acceleration, that's when you have to think about work and energy. Now that's what she's doing right. Now the truth is, and I say this with all total due respect, I do think the number she got there was like different from the number I'm getting here. I think this number is right. And I know what the mistake is that she made. I don't want to put it that way, but I know what happened. It's that when she did work, she did force times displacement, which is right also. I mean, that's correct. Work is force times displacement. But I'm going to say this one way a little bit quickly now, and then I might say this in a longer way in a few minutes. Work is force times displacement, right? But what's tricky here is that we have a changing force. We have a changing force. The force might be 200 newtons per meter times 0.15 meters when the block is all the way extended and stretched at 0.15 meters of displacement. Like right at that moment, right at that spot, the force is 200 times 0.15. Right? But then the block starts coming in and coming in and coming in, and the force gets smaller and smaller and smaller and smaller until the block is right at the center at x equals 0. And at that moment, the force is nothing at all, right? So she is totally right. And again, I'm going to say this in a longer way to everybody. This is not her bad. This is like kind of the trickiness. This is a trickiness of variable forces. This is where, in some ways, those of us who have some calculus, you might see where the calculus comes in. I'm not forcing you to do calculus, or I'm not saying you have to do calculus, but you could start to see why calculus is one way of looking at things, because work is force times displacement. Or put another way too, this is why I had to make a big deal in the video of like, well, it's easy to calculate force times displacement where you have a small enough displacement that you just have one force number to multiply, to plug in. If you just have a little bit of displacement, like right at the edge here at 0.15, if the thing doesn't move very much, then the force is 200 times 0.15. That's the force. The displacement is 0.15. Okay, we multiply them, we get the work. But as this thing is moving, the force is getting smaller and smaller. So it very quickly becomes no longer fair to say that the work being done is, or it's no longer fair to say that the force is 200 times 0.15, like a little bit in, it's 200 times 0.14, then it's 200 times 0.13, then it's 200 times 0.10, then 200 times 0.05, et cetera, all the way down to the center where the force is literally 0. So what is the work? How do we know the work being done for the whole thing? Well, one fast thing I could say right now is, we're going to have to average. If you don't want to think about it in the calculus terms, you could say, well, out here, it's 200 times 0.15 is the force. Here at the center, the force is 0. So if you want to be, and it smoothly diminishes all the way from this extreme to that extreme. So if we took 200 times 0.05, that would be too big. If you took 0 times 0.15, that would be too small by the exact same margin of error. 200 times 0.15 would be too big by exactly the same amount that 0 times 0.15 would be too small. So one thing we could do is take the average. We could take 1/2 times 200 times 0.15 as the force and multiply that by the displacement 0.15. In other words, instead of doing kx times x, which is honestly in effect what actually Yulia is doing in hers, it seems reasonable for saying work is force times displacement. It seems reasonable to go, oh, well, if in this case the force is kx, then do force times displacement, kx times x. That seems reasonable, except that the x is changing all the time. So actually, what's most correct to do would be 1/2 kx times x, the average force times x, i.e. 1/2 kx squared. Now, I kind of said that all too quickly, but I also kind of took too long to say without writing anything down. What I'm trying to say in the end of the day, I will show you again a little bit later, and I'll show you based on the video I was doing last time. What I'm trying to say is that's where I get 1/2 kx squared from. 1/2 kx squared is the work done by a spring. The 1/2 comes from the fact that if we just said kx times x, if we just said kx squared, that would be the work that the spring would do only at that spot all the way on the outside. It wouldn't account for any of the spots toward the inside. It wouldn't account for the equilibrium spot. If we want to be proper about it, we could think of it as an average 1/2 kx squared. Or if you know calculus, if you're going to see what I'm going to show you, if you think about it in a calculus way, you could think of it as the integral of kx dx. And the integral of kx dx is 1/2 kx squared. Again, for some of you, that's like an annoying thing for me to say. For others of you, that might snap it into focus. I'm ultimately saying that the work done by a spring, and therefore the potential energy stored by a spring is 1/2 kx squared. The slight error that I think Yulia made in her calculation, she did everything logically right. The whole right method and everything, whether it looks to you like she's doing the same thing or not, she is doing the same thing that I'm doing. It's just, I think there's a 1/2 missing in there for this subtle reason that I just said. So this is actually the answer. I'm going to say two things about this, and then I'm going to move. I mean, I will go back and revisit that 1/2 again if it confuses any of you. And I'll show you how it connects to the lecture I was doing, on tape 2 days ago. But let me also say, because I keep talking about Yulia, and I don't know if it's like I don't mean to put her on the spot or anything, but I am so pleased that she did volunteer this at the beginning. Oh, okay. Oh, cool. That's so nice. Okay. She just got about 100,000 points. Let me tell you why. And again, I'm not trying to overly praise one person or pick on anybody, but Yulia just got 1,000 points. Here's why. First of all, she did, tonight, when you submit your game terms, when all of you submit like what you did just today, and you all get 5 points, like, she can remind me that we had this whole conversation today. That's 5 points right there. Also, she's going to submit that in the port, and I'm only saying this as an example to all of you so you all see how this works. It's not just Yulia, of course, but if any of you ever submit a screenshot of any kind or an image into the chat like she did, you'll notice there's a portal that's called something like an image is worth 1,000 words, or so. I totally forgot what it's called. I think it's called an image is worth 1,000 words or something 1,000 words. And there's a portal where, and just find it, one of the game portals where anytime you submit an image into the chat, you just remind me of that fact and you get more than 5 points. You get like 8 points or 7 points or something. Okay, so she did that. But also now, this is the thing I want to explain. Oh yeah, yes. I totally see. Yes, it's a direct chat, so I won't say the person's name. But yes, any of those participation game things that say like October 1st on them, if that's what you're talking about, even if I forget to change them, don't worry about it. Later, you could submit any of this image stuff or whatever, even if you submit it after October 1st, it's totally fine. That was just meant to gently push us along or whatever. Don't worry about that October 1st deadline, please. I will try to change it if I remember. But yeah, so you can submit into the image thing if any. And that also means, right, like if next week one of you submits an image, you totally can get the, oh, okay, good. Thank you. Okay, that's, and then you just, okay, so the person in the direct chat just got more points too. Oh, okay, and I'm gonna get to Shasha's thing because it's public in 1 second. Let me just again, not to belabor this, but I wanna make something clear because I put a new portal in today too that I wanna clarify for everybody. So I'm gonna continue to use Yulia as the example here, but it's just an example. First of all, like whatever she did today, she just reminds me quick, oh yeah, I'm the one that gave you the screenshot of the energy thing. So blah, blah, blah. So she puts that in for 5 points. Then notice I went on and on and on and talked about it for a million thousand years, but eventually, wait. So she puts it in the 5-point thing. Then she also puts the exact same, she doesn't have to change it or anything. She takes that same little reminder and she puts it in the portal that's for screenshots and images, whatever it's called, worth 1,000 words. Then, so that's 2 right there. Then notice I talked about Yulia for 1,000 years, went on all this. Now, I don't know if I'm upsetting her or embarrassing her or if it's helping her or not or anything, but finally, somewhere Yulia wrote in the chat, like, thank you for clarifying or something. She wrote, thank you, which tells me that she's been hearing all this and she's good and it's all cool. And it tells me that she's not upset and it tells me that it's clear. So she closed the conversational path, right? Like she brought the conversation full circle and closed it. So she could take, again, that same thing, that this whatever entry, and put it in that portal for even more points. That's so far, that's a triple dip. But let me go even further now on the new thing that may not be clear to some of you. Notice also that she actually, it's not just that she submitted an image or just some random thoughts. She actually had the guts, and it's not just her. Obviously, other people have been doing this too, which is great. But she had the guts to actually submit. If you look at the screenshot that she put, she has specific numbers there. She worked out a homework problem there. She actually has an answer that is gutsy. And she was leading me to a situation where I would either ultimately say that answer is right, or I would say it's wrong. But it's concrete enough that I would say one thing or the other. Therefore, she puts that also in the portal that's called for right or for wrong. Like literally anytime anybody says anything or puts anything in the chat that is specific enough, concrete enough, gutsy enough, risky enough, that you're risking that I'm going to say it's right or it's wrong, you put that in the for right or for wrong portal, no matter whether it was right or wrong. Like I'm trying to say to people, I don't care whether something's right or wrong. If you're gutsy enough to say something that might be either one, God bless America, Quark bless America. But now, I'm going to go, what? So that's a quadruple dip right there. That's that many points for just one thing she did. But now here's the ultimate capper that I really want to stress to everybody. The new portal that I just put in today that I think says technically due November 1st, but whatever. It says be wrong, be really, really wrong. That one is like the weirdest portal of all. That's saying if you ever do anything at all that was gutsy enough or risky enough to potentially be wrong, and I literally come out and say somehow that it's wrong, like hopefully I say it in a polite way. And hopefully, like, I make it clear that I still think it's a good contribution, yada, yada, yada. But if you actually go on a limb and say something specific enough that it actually leads me to say in public to everybody, that's not totally right, or that is a mistake in step 5, or it's misguided here, then I think that is so important and so good for everybody. And I want everybody to know that wrongness is not wrong, if you know what I mean, right? That you can take that, even though you've already gotten points for the fact that it was gutsy enough to be right or wrong. You already got points whether or not it was, whether it was going to be right or wrong. You get points for it being that specific. Now, the fact that I actually did come out and say for all of this, as much as I'm raving about Yulia's whole thing, I am admitting I think that she did make a mistake, or she left something out, or there was something wrong in her final number, because I think that, and it's not a criticism of her, like she couldn't have known, but like because she didn't include the 1/2 in kx squared, she just did 4 times displacement, then she's going to submit that in the portal that says be wrong, really wrong, and she gets 11 points for that. Now, and oh yes, now I'm looking, now that's crazy, that's so unusual, that's why I'm spending so much time talking about it. I'm literally telling you all that you get extra points for being wrong in this class. Like I am literally saying that. Let me look at Kwan's thing. Yeah. Oh, no, good question. No, about your work, like if you, about physics, I'm saying, right. I am saying what Hannah, that's right. Like I'm saying, if you ever submit any physics, I mean, it could be about my work. I mean, honestly, it could be like if I put up a homework and you think I made a, I think, did this happen in this class yet? But like, sure, it could be about me. Like if you think I made a mistake somewhere in the work and you like go out on a limb and say to anybody, professor, you said over, or my solutions, like if you think I made a mistake here, like whatever, it could be about my work, but I'm not really saying that. I'm saying that if you do some physics, if you volunteer an answer, if I ask you all a question right now, if we go on to question 5, and I say, does anybody have a thought about the final answer or about this step, how would you do this? Anybody who volunteers anything that is gutsy enough and specific enough that then I come out and say, that's wrong? That, oh, good, thank you. Okay, by the way, you understand that Quan just got points for closing a conversation, right? Quan asked a question, I answered it, and then Quan said, oh, got it. Okay, we're cool. So that's closing a conversation. That's points right there. Also, I think that also for Hannah, like she closed the conversation by like, maybe I should call that something different. But as far as I'm concerned, Hannah just also acknowledged the existence of somebody else and sort of like acknowledged that something else was going on and tried to clarify for that. So that could, help shut that conversation down. But yes, what I'm literally saying here, and this is unusual, that's why I'm screaming it. It's so unusual. Even I've never done this literally before. I've always wanted to, but I don't think you have this in other classes. I'm literally saying that you get points, extra points for being wrong in this class. Now, if you really hear what I'm saying, and it sounds like Quan does, and it sounds like Hannah does, first of all, I am saying it does apply to at least part of what Yulia did. Like now, but I'm trying to say, the whole reason I'm saying this is, I don't think what Yulia did was wrong. Like it was great. It's totally a great contribution. There was one mistake in there, or put another way, there's something, if you do, it's such a great contribution. I want you to look at her screenshot, but you might get confused if you see that her answer is different from mine. So I have to come out and say, well, in the end of the day, her answer is not quite right. Please look at my answer. But that's very risky of her to put herself out there like that. And what I hate about science and science education a lot is if I say that enough, that her answer is wrong, please look at mine. It's so discouraging. It makes it seem like she shouldn't have done that. It might make her regret doing that. And that is not the message I want to send. I want to say, no, we are scientists. We experiment. We experiment in public. We are willing to make mistakes in public because that's what we do. And then our mistakes are more productive than our like perfectionisms. Right. So I'm literally saying in this class, if you do something that, and the other thing is we also know, I think some of us have secretly noticed that I have a little bit of trouble sometimes coming out and saying that someone's wrong, or someone asks me a question. I don't, like even my son, I have a hard time kicking out of the room, you might have noticed, right? I'm not so great at saying people are wrong and they're wrong because I really think that they're like very right, even when they're wrong. So also what I'm kind of saying is like, I want to also help you help me come out and admit when I think there's a mistake somewhere. And the way we're going to do that is you get extra points when you're wrong. Now, by the way, if you're really following what I'm saying, you might think, wait a minute. Okay, that's a little wacko. Like, what's to stop me from just like raising my hand and saying dumb shit? Like, why wouldn't I just like raise my hand and say 2 + 2 = 5 and get extra points for that? Here's my answer. I dare you. Like, go for it. Like, let's see. Right? Like I'm not worried about that. I mean, I think maybe people might occasionally do that and fine. Even if it like makes the class funnier, fine. You get points for doing that. Like I would actually love to see anybody with the guts to abuse this system and be willing to be publicly wrong so often that they get a ton of points. I don't think science students could do it. I think we're in such a climate of, especially not on Zoom, it's just we're in such a climate of perfectionism and like inhibition. So if you're actually sitting there thinking he's giving points for being wrong, so I could just like be wrong a lot and get a lot of points. Yes, that is what I'm saying. I mean, you have to go public with it, but okay. Is it? Okay. Thank you. Okay, I see the private chat. Thank you. I totally get it. Thank you, the direct chat person. Got it. No problem. And you can pass that. Okay, so that was like a little long speech, but But honestly, also, and there's a last time I'm going to mention her name for today, but Yulia's thing today is like the exact perfect example of why we need a system like this, because what she did is like such a good contribution to the class. It helps the class so much, and it helps me clarify issues both, and she's 99% right, but even where she's like slightly wrong, also totally forces me to clarify issues for everybody and blah, 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 blah. It's such a right thing to do that I want you all to see that. And I don't want the little bit of like wrongness or whatever infect the larger message. So I'm literally saying the contribution, for example, that Yulia made today, she can quintuple dip that. She can put that in that one entry in 5 different portals and get all those different points for it because that's how strongly I believe in all this. And of course, that wouldn't be fair, except that it applies to all of you. You can all do that. And don't worry about the deadlines. Okay. Having said that, oh, cool. Oh, see, well then now I love the system even more. This is so great. Okay, no, cool. Now I'm going to go on to the next. And I know Yeah, cool. All right. No, I'm glad. I really am glad. I'm very glad. Okay, so I'm going to go to the next question now. I'm going to do it a little bit faster. I'm going to try. I know. Go to oh. Yeah, I'm sorry. No, that's a fair question. Oh, I should almost get points for that. Yes, very soon. I know I keep falling behind because of the other class. This weekend. This weekend, I think. I'm sorry. And of course, that's a first draft grade, because then even if you don't like your grade, you could still do more and fix the grade. But yes, I'm pathetic. I have fallen way behind. This weekend is the answer. I'm so sorry. But yes, this weekend. Okay. And thank you for saying thank you. That's closing a conversation path. That and well, yeah, okay. Yes, but my bad. Okay. So now I'm going to go on to the next question. I'm going to start trying to speed up here a little bit. And luckily the next question, we do just like that question. Like the next question will be a lot easier. There's no new concepts in the next question, really. It's just oh God, Sasha had a question a million years ago and I totally missed it. Wait, I'm sorry. Hold on, I'm sorry. Right. Is it the same? Did you copy paste? Yes, I'm so sorry, Sasha. That's bad. You should get points for that too somehow, for being patient and nice about the. Do we need to write all the units in our calculation? They didn't say. Oh. No, that's a very fair question, and that almost. Okay, so my fast answer is yes, you really should write out the units. You should write out the units. And did I not over here? Let me see. Oh, like in that you're right. I was being a little, I went a little fast in because I was getting afraid that I was getting all over. Yes, please do units. And when I don't, that is bad on me. Or maybe I'm making a choice to be a little shortcutty to move on with it. But yes, please do units. Yes. Yeah, okay, no, fair enough. And that counts as closing our conversation path. And I'm almost tempted. Well, yeah, anyway, no, that's a very good question. And you're right. So in this next one, I will try to put in the units. Okay. So question 5. Okay, same diagram. I'm just going to draw the diagram quickly just because it's the same diagram, but I'm going to draw quickly just to model good behavior. And also because I've been talking so much, we might have lost sight of what the heck is going on. Right, so that's the same diagram. Okay. So now no. Okay, as I said, I'm gonna try to speed this up, this one a little bit, but notice the last question was when x equals 0, what is v? This question is when v equals 3, what is x? It really is the same type of question, just in reverse, right? In other words, what I'm saying is, oh, wait, sorry. quick note, what I'm saying, and this is, by the way, part of the reason that it's always important to like jot down the question in your own words before starting to solve it, is when you jot down the question, especially in your own words, or especially in some sort of abbreviated, concise form, you start to see things about the question that you don't otherwise see. Like when I just get in this habit of just writing like, when v equals what's x, I suddenly notice, oh, you know, even though it looks like a totally different question, really, like the last one was like, what is the speed attained by the mass when it reaches equilibrium? And this one's like, at the moment that the mass has an instantaneous speed of 3 meters per second, what location does it arrive at? Like in English, it sounds like a totally different question, but really it's the same question as before. What we're driving at here is a correspondence between speed and spot. The whole assumption here is like, if you name the spot, I can name the speed, or if you name the speed, I can name the spot, right? That business is the nature of energy conservation. Like we're going to say the exact same principle here that we said a second ago for question 4. I'm going to say, and I can turn back the page if you want, I'm going to say, what I'm really just trying to flesh out here, again, it's the same concept as before, but now that we've looked at the concept, I want to just like emphasize what it really is. Whenever we say energy is conserved, like, because again, with the thing that Yulia said before, like energy is conserved in the universe in a very big, broad way. Like energy is never created nor destroyed. That is true, and that's really important, and that's really interesting. But when we say in certain, but that doesn't mean, but that doesn't mean that in all problems of physics, mechanical energy is conserved. Like when friction does work on a system, or when the normal force does work on a system, or when tension does work on a system, energy is conserved in the universe, sure, like, but it's not in that system. When friction does work on a system, it will take energy away. It'll do negative work. It'll slow down the system. And then that energy we can account for in the universe by saying it gets dissipated in the form of heat. But that doesn't help us solve the problem of that system moving along. Like whatever 1/f mv squared it loses, it doesn't get stored as potential or anything. We can't make any predictions about its resulting speed if there's this loss due to friction. Right? When we use energy conservation as a problem-solving technique, when we say, aha, here we're in one of those specific situations where all the forces doing work are conservative, like there's no friction, there's no tension, there's no normal, and we say, aha, someone's telling us the speed over here, and they want to know the speed over there, or someone's telling us the speed over here and they want to know where it's going to be when it has a different speed. Okay, that's a situation of mechanical energy conservation, like the very specific thing that we're saying here of energy, mechanical energy, the total amount of kinetic and potential is going to be conserved from place to place. Like what we were really saying in the last problem, and I'm going to say it again here, is when we apply the theorem of energy conservation, what we're really saying is KE plus PE sub A equals KE plus PE sub B. We're saying the total amount of energy at this place is the same as the total amount of energy at that place. That is and that's why we always use it when what we're comparing is two places. Like so I say energy is conserved from place to place as opposed to time. Energy is not conserved from time to time. The truth is there is something that's conserved from time to time. That's called linear momentum. just as a sidebar, linear momentum is conserved from moment to moment, but mechanical energy is conserved from position to position. So whenever people are comparing two positions in a problem and wanting to know the corresponding speeds, that's when we use energy. So, okay, blah, 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 blah. So I'm going to do the exact same principle that I did in problem 4. I'm going to say, so oh, whoa, hello. Whoa, sorry. Right, so just like before, energy is conserved from spot to spot. One spot is a spot where you know everything, i.e. you know the corresponding speed. The other spot is where you don't know what you're solving for. So last time what we didn't know was what is the speed at the other spot. Here, we're actually looking for the spot itself. So again, I'm using a known spot of x equals 0.15 where I know that the speed is 0. Frankly, well, anyway, so I'm using that as my known spot again, just like before. Now, the unknown spot is literally the unknown spot, the spot that I'm solving for, x. I don't know it. But I know that at that spot, the speed, according to the problem, is 3, right? So now I have all the information. So okay. Sorry. So now even though I'm over talking this as usual, I'm doing the exact same thing I did in problem 4. And note, it's a totally different question, but well, it's not totally different, but it's a different question, but I'm starting with the exact same process as I did in question 4 because the same general definition or principle or concept applies. Question 4 was about energy conservation. Question 5 is about energy conservation. So I start with energy conservation. I start with something true and then I make it relevant. I don't start with something relevant and then try to make it true, right? So, okay, so going to the next page. So now I fill in. So kinetic energy is always 1 of mv squared. Again, if you want me to explain why that is, if I haven't, please let me know and I will. Then spring potential energy is 1 of kx squared. I kind of did explain that before, but I didn't write any of it down. That might have bothered some people, and I will revisit that. I will, but oh, no problem. Totally understood. Thank you. No problem. Private chat person. Surprised it doesn't happen all the time. Okay, so we have this now. Now notice, still looks, and this I really do want you to see. Notice that it still looks exactly the way it did in problem 4. It's all, even though it's a different question, it's all about energy conservation. But now we're going to start applying it to the particular situation. So I look at spot A. Spot A was the place where the position was 15 centimeters. So at spot A, V was 0. Right? So I can cross that out. right? But now I look at spot B. I look at spot B, see if I can cross anything out there. Spot B is the X that I don't know that I'm solving for. So X is certainly not 0. It's not the equilibrium. I know it's not, it's somewhere between the equilibrium position and 15 centimeters, because it's the place where the speed equals 3. And I know the speed is 0 at the edge, and I know it's 3.87 at the equilibrium. So it's somewhere. So anyway, X is not 0, so I can't cross that out. And V is not 0 because V is 3 at the spot I'm looking for. So I want you to really notice now one thing here. I'm starting with the same principle as question 4. And a lot of you knew to do that. A lot of you did do question 4 and question 5 the same way. But a lot of you, and I do know this even though you haven't gotten your homeworks back yet, a lot of you got question 4 correct for whatever reason. But then question 5, you did the same way and you didn't get the answer correct. And the reason I just want you to note is that we don't, by the end of question 4, it looked like we were saying 1f mv squared equals 1f kx squared, and then we solved. But that was by the end. We didn't start by saying 1f mv squared equals 1f kx squared. Like, that is not a general principle or a truth. A lot of people think that by the time they get to the stage of physics. A lot of people look at energy problems and think, oh, it's an energy problem, so kinetic has to equal potential, so 1f mv squared equals 1f kx squared. That is not a thing. It looks like that's a thing, but that is not a thing. Like, we're never saying kinetic equals potential. We're saying the sum of all the kinetic plus all the potential over here equals the sum of all kinetic plus all potential over there. And then we're crossing out whatever we can depending on the situation. So sometimes we get lucky and we cross out enough that we end up finding, oh, kinetic over here equals potential over there. That's what we ended up saying in 4. Ended up saying. Here, we're saying potential over here equals the sum of kinetic plus potential over there. Like, basically, I'm just trying to say, we have crossed out as many terms as we can cross out for this problem. We can't cross out any, I mean, we could cross out the 1/2, but we can't cross out any more energy terms. So don't ever memorize or think kinetic equals potential. That is not what we're saying. And we're not saying it here. Anyway, I think you get my point. So I'm also gonna, but I can cross off the 1/2. That I can do because you can factor out the 1/2 and divide both sides by the 1/2. So now what I have, okay, just to be clear, now what I have is kx squared over here at spot A equals mv squared plus kx squared over here at spot B. And notice another thing I guess I'm trying to say is we have kx squared on both sides. So if you're not careful with this, or you don't actually see what I'm saying, it's very easy to think, oh, the kx squared is like subtract kx squared from both sides, they drop out, and then what we have mv squared equals 0, like what? But no, it's 2 different kx squared because it's 2 different x's. Oh, chat, sorry. Oh, yeah, so, okay. Right, so soon we're gonna plug in numbers, but I'm not ready to plug in numbers yet. Like, what am I looking for? I'm looking for living all the wrong place. No, I'm looking for x, specifically x sub b, right? The other x is the known x of 0.15. So I'm looking for x sub b, right? So I'm going to rearrange. Right? And now here too, you might think, I don't know what you might think, but I can't divide out the k's. I cannot get rid of those k's because I can't factor them out from both sides. I don't have a k in every term. So the k's have to stay there, right? But I'm looking for x, so I'm looking for x. So oh yeah, this is the point where some people will sometimes think you can cross out the k's, but you can't. You can't cross out the k's unless you had one in every single term. You have to be able to factor it out to cross out. I don't know if that makes sense, but you can't cross out the k's. So now I say this. Oops. So I'm going to go on the next page. Okay, I'm going to go to the next page. And I'll try to be careful about units this time. Ah. Right. Now I can plug in the numbers. Wait, what did I do? Oh, yeah. Right. Oh, no, sorry. Wait, sorry. Oh, my bad. Wait, I see what I mean. Sorry. This is not. Right, sorry. Oh, I did it both places. I forgot the square. I'm so sorry. So I get 11 points here for being wrong. But
That is so funny, Professor. Is that points?
well, you're very kind. Well, yeah, but I want them. I want them. Well, thank you for following along. I can't believe you're still following this. That's great.
Oh, I'm taking notes because I want to correct my homework.
Got it. Aaron. Okay. Now I think we're okay. Yes. Okay. Now we're talking. Now, a couple of things. This is the answer, the thing that's on the, yeah, that is the answer. And just for the record, also, when I was saying a second ago, like that I made an error and I got 11 points, what the errors that I was making was in the numbers under the square root. And I knew those were errors of some kind because I did know what the final answer was supposed to be and it wasn't working out. In other words, what I'm saying to everybody is the final answer is definitely right. And this is all right now. But even in the middle of what I was saying, oh, I'm making a mistake, like don't lose confidence. Like this is the final answer. And the reason I was trying to be very careful and put in all the things is honestly because I love the fact that I think it was Shasha, because Shasha asked about units, and it is true. Now that I'm thinking about it, sometimes I do get fast and loose when I'm going over these solutions. Like sometimes if the things look complicated enough, I will get careless or inappropriate and leave out the units when it starts looking too complicated. But she's absolutely right that the more complicated it looks, the more it really, really is good to put the units in, because the units force you to see whether you're doing things right or not. In other words, it's because of these units that I was following the particular individual numbers and knowing that I was doing something like wrong with them totally because of the units. Let me tell you what I mean. Oh, sorry. Okay, but I'll shut up for a second. Alex, yes, I'm sorry, Alex. I think.
So if we're doing our homework and we're writing out our work, if we have a specific point where we're like, I don't really know if I did this part right, could we like write out a question? Like when you give us back our homework, would you answer those questions if we wrote them out?
Yeah, that's a great question. So the fast answer is yes.
Okay.
Yeah, I mean, this is my brother would say. The short answer is yes, and the long answer is yes. No, I'm just kidding. I mean, no, here's the deal. Like the answer is yes, but let me expand on that for a second. To everybody, it's a great question. First of all, yes, whenever you're in your homework, if you reach a stage, especially like I just did, if you're doing things out carefully enough that you can get to a step and be like, I'm not sure what's happening at this step here, or like I'm doing it, but I think I might have a mistake right here in this step, or let's even be more realistic. Maybe this is even what Alex is getting at. Let's say you were doing this step and you kind of did know what you were doing, but then you tried to include the units and then the units got all funky, which is like kind of what happened to me here. You could totally, you don't want to like be punished for, like you can and should totally do what Alex is saying and write something like, wait, can you help me here? Or I don't know what's going on here. Now, so it's definitely yes. Even if I take a really long time to get the homework back, or even if I miss that you did that and don't respond, but I will eventually, but even if I don't respond fast enough to help you iron out that part, that is still a super important, super great thing to do, because frankly, you can and should even do that on exams. The reason I like the fact that Alex said that so much, and this is points, I think he gets triple dips these points or whatever, is like, if you can do out your homework in step by step specifically enough that you can literally isolate steps and say, it's at this step where I'm having trouble. Like, even if I don't answer, and I will, but even if I don't answer your thing right there, that shows that you've now subdivided the problem so sufficiently that you, like, basically what I'm saying is, if you can diagnose your own difficulty to that level of specificity, if you can break down a problem enough to know exactly where it is that you need help, you've already done 90% of the hard work for you and for me. Like, part of the reason we do all this, show all your work, do all the steps, is precisely to get everybody to that point where they can actually see where it is they don't know what's going on. Like, that is such an important part of the whole process. So yes, okay. All right, cool. So totally yes. Okay. Now, I also want to get back to this shot. So this is the answer to this one. Oh, no, cool. And so, by the way, you realize, I hope you all realize that Alex just got even more points for saying thank you. That helped. I know this is just like point fest. Again, it's all Nook miles in Animal Crossing. That's what this all is, if you know what I'm talking about. Like, I love the thing that's hilarious to me, if you know what I'm talking about. Like in Animal Crossing, you get Nook miles for doing this. You get Nook miles for doing that. And then you even get Nook miles for cashing in your Nook miles. It's like ridiculous. They're just like, it's like a total, like we reward every system. Like they even give you, and if you don't know what I'm talking about, it's a video game. And it's just like, you get these points for doing all these things like and you get points for, yeah. Wait, let me see. Hold on right here. Oh, sorry. Okay, I'm going to stop raving about video games for a second. But great question also in the direct chat. I'm not going to read the person's name because it's direct chat, but I will read the question because it is a good question. She or he says, when we get the answers and get a long number, is there a certain number of significant figures or decimal places that I want our answers to be? That's a very fair question, especially this is a science class and all that. So now I have two answers to that. I mean, first of all, you have to be a little bit more careful about significant figures and decimal places in the lab portion of the class. Like, I mean, you can be a little bit more casual and flexible about them here. Even on exams, I can be a little bit casual or flexible because this isn't the lab component. However, here's the we don't have to get totally hung up on them, but here's the basic rule of thumb for sig figs. You should express your answer to no more significant figures than the original numbers in the problem were presented to. That's the basic rule. Like the basic rule of thumb is go to as many significant figures as the given measurements go to. Like pretend the numbers I gave you in the original problem came from measuring equipment, then that's telling us how many significant figures we can measure to. So basically like, yeah, and I guess I'm being maybe not even perfect about that, but like there's no reason to go to 4 significant figures here because, oh no, I am being proper about it, right? Because the 3 numbers I gave you in the original problem were 200 newtons per meter was K, 0.15, which I guess I technically should have said 0.5150 was X naught, and 0.3, which I should have said 0.300 was the kilogram. So the greatest number of significant figures I gave you in the original problem was 200 newtons per meter. So I'm trying to put all my answers to 3 significant figures. That's the basic rule of thumb. I mean, okay, cool. That direct chat person who shall remain nameless also just got points for closing a conversational path, but she or he shall remain nameless. But okay. One last thing I was trying to say about Sasha's good point about units. Sometimes units are hard to keep track of. And by the way, also, like, you should, it's good practice. The more you pay attention to unit, the more you can see. Like, excuse me, the harder it is to make the units work, the more that actually is telling you, the harder it is to make the units work, the more actual information the units are giving you about your computation. So it's like, it is worth it, even if though sometimes I'm casual about it. So even if you look here in this computation, like K is in newtons per meter, X is in meters. So I have newtons per meter times meters squared, right? So that's why the meters like flipped, like, so one of the meters crossed out, but then I had another meter up there. I have newtons times meter in the denominator of the square, 4.5 newtons times meter, right? Because it was newtons per meter times meters squared. Then I had kilograms times meter per second squared. How did I say that was Newton times meter? Well, F equals ma. F net equals ma. Forces are masses times accelerations. So a unit of force, the Newton, is a kilogram times a meter per second squared, right? A meter per second squared, acceleration. But what I had there was 3 meters per second, all of it squared, right? So technically I mean, maybe I'm doing this too fast in my head, but it wasn't BS. Like I'm saying a kilogram times a meter per second squared times another meter, which is what I have there, is a Newton times a meter. And that's good because you can't, I mean, both those units had better be the same. Otherwise you couldn't subtract one number from the other. You can only subtract like units from like units, right? And then in the bottom, in the numerator and the denominator, we had newtons per meter, right? So you see like the newtons all crossed off, and then the meters flipped up. So I had meters squared, which is a good thing because then I square rooted it. So I got meters. I mean, I don't know, I guess I didn't have to explain that, but that's what's going on there. So it's really good that Shasha actually, and again, if I hadn't been tracking those units, I wouldn't have realized that I was BSing the numbers. So it's like a good thing. All right, anyway, that's okay. Oh, sorry, I totally missed. Oh, sorry. Oh, very well. Wow, great. Okay, so both Shasha and Kazi get like points up the wazoo. It's a point party, and they're getting tons of Nook miles too. Yeah, it's a great question on Shasha's part. It's a great question, and it's a good answer, a great answer. Here's, I mean, and then this is a slightly technical. I will tell you too, if on the homework you didn't do this part, I wouldn't even notice it or take off points. Like if this were an exam, I'd have to be a little bit careful about this. But yes, technically, I'm keeping both the positive and negative answers. Here's why. Well, I mean, mathematically, I think you all know that you technically, mathematically, there are the two roots. And always, whenever comes up in the math, always means something in the physics. But then the question is, does it mean what the question's asking us to care about? Like Shasha's question is a very valid one, because just because the math returns two roots doesn't necessarily mean that both of them correspond to what we were looking for when we asked the physics question. But here's the deal. What I think, and you look at the sheet, but I think the physics question said, at what position do we find the mass when the speed, instantaneous speed, is 3 meters per second? I think that is what the question said. Now, the speed could be equal to 3 when the object is moving a certain way with a velocity of positive 3, or the speed could be, okay, cool, thank you. And that's totally bringing a conversation. That's points, more points. That's bringing a conversation full circle. Thank you, I totally appreciate it. So yeah, so if that's what the question said, I mean, given that that's what the question said, if it said when the speed is 3, that means the velocity could be positive 3 or the velocity could be negative 3. In either case, the speed is 3. So we are looking for the spot where the object is moving like to the right with positive 3, with a speed of 3, or we're looking for a spot when the object has that same speed but moving in the opposite direction. In other words, it could be the spot on the right side of equilibrium, or it could be the spot on the other side. Either way, the speed would be 3, either way. So I think technically, actually, both of these answers are valid for this question. What I'm really trying to say, but again, this is why it's a valid question on Shasha's part, because if it's not like just automatically whatever the math spits out, we always care about. We have to look at the physics question. If the physics question had said, find the spot where the velocity is positive 3, then I think we would have only taken one of the two answers. But it said speed, so we're taking both. I mean, I think that's my answer to that. Now, let me just look at the time. And this ends at 5:45, right? Okay, well, still got a little time. Sorry to say. Oh, okay. Oh, cool. Oh, cool. Cool. I like the 0880. Okay. That's, it's so weird that spelling. I could tell. That's so interesting. Okay, right, cool. Okay, so that she just got more points for closing the conversation, blah, blah, blah. Okay. Okay, so I'm going to go on to the next question. Hopefully I'll go a little faster. Hopefully. Now, look, again, actually, I'm going to pause for a second because I know I'm taking a while with this, and I always take a while at the beginning of the semester, and I apologize. I just think it's all about fundamentals, and the more clear we are on fundamentals, the more fast we can go on our own. I really do believe that. And the more fast we can go as the course progresses, the more I think we're grounded, the more I can expect us to move faster with things. But so I know I'm taking a while to go through the very first homework. And quite frankly, the very last question on it is going to take us a while. And I'm going to have to make some adjustments. That the last question, there's no way we're going to finish today. We just aren't. But therefore, but I think we'll finish everything else today. In fact, I know we will. Yeah, we'll finish 6, 7, 8. Yeah, in fact, I'm going to write down the answers to 6, 7, and 8 in 1 minute. So even if we don't get to explain them all, you'll see all the answers to 6, 7, 8. But I have to ask a question. what's the very last, the most recent thing you did in lab, which I guess was Monday, no, or yesterday? Could someone just tell me in the chat or with voice, whatever, like what did you do in, what motion did you do in lab yesterday? Motion 3, okay, okay. The pendulum, okay, okay. Okay, pendulum motion 3, okay. So now you're a little bit ahead of me in lab, which is good. I mean, lab should always lead lecture a little bit, but I do have to make some track. So I'm gonna try to close the gap and catch up to you guys. Okay, good to know, good to know. So I think in the interest of that, I'm gonna write down, I'm gonna stop talking. I'm gonna try to stop talking for a few minutes. I'm just gonna write down what I think the answers / solutions are to the next few problems, maybe even including the last one. So even if I don't get a chance to talk about it, you can at least see. Okay, so that's what I'm gonna do now. I guess I said I was gonna do that before and I kind of didn't do it, but okay, so. Oh, unless there's any question, but stop me if there's any questions. I'm just trying to stop myself from talking so much, but stop me if there's any questions. Okay. So that was 5, okay. Oh, sorry, and last thing, the overall summary of question 5. Notice I got the answer 0.095 plus or minus 0.095 meters for question 5. Like that is the answer. I mean, that is the answer. And I just want to make it clear that if you got an answer of 0.116, which is a very common wrong answer, if you got 0.116, no shame, no crisis, no problem, but I do want you to know that's not a rounding thing. Like that is wrong. If you got 0.116, that means you just wrote 1/2 mv squared equals 1/2 kx squared. And I'm not saying there's any shame in that or anything, but that's the one thing I want you to note. Like that's the error I'm trying to caution you against. Don't just say 1/2 mv squared equals 1/2 kx squared. It's like not the case. So if you did do that if you handed in your homework and you did that, you could still change it and you'll get all the points back. Like, don't worry, but just know the answer is 0.095, not 0.116. Okay. Okay. So that's question 5. Now question 6. Question 6 is the one that says, right, I believe this is a question where, well, I'm just going to. Okay, I'm just going to say, I want to move on. I'm saying for that, I think most of you got this right, and most of you know, and most of you might not have written much work or even written anything mathematically. You might just like visualize it in your mind. And I'm not saying you're wrong. You're not, if you're just thinking, oh, well, the next time the object stops, like when it gets as far as it can on the other side, it's going to be the same thing as it was on the first side. If you're just like picturing that this whole situation is symmetric, that whatever's happening on the right side is going to happen mirror image on the left side, I'm saying you're right. I'm saying you're right. If you're just picturing that it's like what's intuitive and symmetric, you're right. But the reason you're right is because energy is conserved. And what energy conservation really means is this perpetual speed spot correspondence, right? So if we ran the numbers again, we would get the same numbers again. Whenever the speed is 0, then the spot has to be the square root of 0.0225, whether that's the plus root or the minus root, and vice versa. In other words, what I'm saying is, sorry. Yeah, actually, good question, Diana. Great question. Just to go back, I am saying if I'm remembering I'm going to go back to it. That is a negative that I'm putting there. If I'm remembering the question correctly, I think the question says like the very next time the mass slows all the way down to 0, like loses all of its velocity in one direction and is about to turn around and start having velocities in the other direction, the very next time the velocity is 0, what position is the mass? And I'm saying, well, if the question did say like, what's the very next place that this happens, it's 0.15 on the other side is the very next place, is negative 0.15. That is what I'm trying to say, if I'm remembering the question correctly. Does that make sense? Oh, okay, cool. Okay. Let me just look at the time. Just a brief side. Well, am I going to take too long? I can't resist saying this. Brief side note on this. Like, again, I'm just trying to say that if you just intuitively were like, the next couple of questions, this question, in fact, okay, wait, yeah, I'll just answer the next question first, and then I'm going to go back and explain what I mean by this page, just so we can make some tracks here. Like, so the answer to this question 6 was negative 0.15 meters, basically implying like whatever's going on the right side of the spring, whatever's going on the is the same thing that's going on the left side. Like if you're just picturing mirror images or some kind of pattern that's just repeating, you're right to do it. And I'm just saying that pattern that you're picturing in your mind, or that symmetry, or that mirror image quality, or that reversibility of the whole thing, that's really what energy conservation is. That's what I'm saying. And I'm even saying it for the next question as well. Question 7. Okay, just stop it. And I think, again, this is not meant to be a trick. I think most people got this right, especially if they assumed it wasn't a trick. You might not have said very much or done very much math to do this, but yes, for the question 7, when it says like how many cycles will go on until this thing stops, the answer is it won't stop. The cycles will keep going on and on forever, especially if we believe the thing is going to go from 0.15 to negative 0.15 and then back to 0.15 and then back to negative 0.15. Then there's no reason. Then if it's always going back to the same endpoints on both sides, then there's no reason. Then the trips are not getting shorter, so they're not tending. So they're staying constant. So it'll go on forever. If you said that, first of all, you're correct. If you didn't give a ton of reasons or a ton of analysis, that's fine. The reason is energy is conserved. This pattern, this reversibility, this symmetry is in fact a pattern, and in fact is a symmetry and irreversibility. But there's one thing I want to say, but yeah, infinite cycles, right? I'm sorry, that symbol is supposed to be infinity. Yeah, the answer is infinity cycles, yes. Now, that's what you're saying, right, Joshua? Yeah. Now, I want to say a couple things about that. First of all, you might think in your mind, like, well, all right, but I mean, all right, well, that's just because it's like a physics class. I mean, like, the spring wouldn't really do infinite cycles. I mean, okay, it would in this ideal world of physics, but like, that's like an exaggeration or an idealization or some sort of Smurf village, like fantasy. Like, it's not really going to do infinite cycles. It's really going to do something else. That may be, you may be right about that to a certain extent. Like, obviously, the crappier the spring is, the more realistic the spring is, the smaller the spring is, the more primitive or cheap it is, the less this is going to be true. Similarly, the better the spring is, the longer the spring is, the more isolated the spring is, the more high-tech the spring is, the closer this is to being true. And we can make springs that last a super, super long time. And the better we make them, the longer they last. But I also want to, but yet maybe it is like an asymptote that we try to approach in practical industrial reality. But I want to say it's not an irrelevant abstraction, this infinity thing. First of all, even if you think the infinity thing is like sort of true, but it's sort of a lie, please understand that that applies in exactly the same way to whatever numbers you got in problem number 4 and problem number 5. Like if infinity is a lie, then those numbers are also a lie. The answers that you got, like 3.87 meters per second, for how fast the thing is going, at the equilibrium position, just because that number is very precise doesn't mean that it's any more accurate than this infinity thing. That 3.87 is only as true as the assumption of energy conservation is true. If the spring is kind of realistic and the energy is not really that conserved and it's only making a couple of trips, then that 3.87 number is not that realistic either. I just want to, in other words, remind us of precision versus accuracy, classic thing at CUNY. CUNY is always really, really precise, kind of like the American federal government and like news programs about the CDC and COVID, all incredibly precise and incredibly detailed, and charts and graphs. And then you have like CUNY incredibly precisely last Sunday releasing a calendar on the web that all said we didn't have classes on Monday and that Tuesday followed a Monday schedule. I don't know if any of you caught that, but certainly a lot of my students in other classes did. I was getting emails all Sunday about like, whoa, wait, do we not have school tomorrow? Like what? And of course, everybody believed that because it's like such a precise calendar. It's so detailed and we're so organized at CUNY. And we put out those calendars like every whatever number of months that, of course, everybody assumed that because we're that precise all the time that we're accurate. But no, it turned out to be complete freaking weird gaffe that meant nothing. And we did have school Monday. We didn't have it. I mean, it's such a precise thing to say that Tuesday will follow a Monday schedule. How could anybody ever say that unless it was like true, is what we think. But in fact, somebody said it and was totally not true. What am I trying? And this happens on the news all the time. It happens with the CDC and the government and the science and the government. Like, don't be fooled. Don't think that just because something is precise, just because we got 3.87, blah, 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 significant digits in it, that means that question 4 was somehow like a reasonable, accurate answer without any exaggerations or idealizations being built in, but that this is a lie. Like, no, this is like sort of a lie, but it's only as much of a lie as question 4 was. It's only a lie or a truth to the extent that energy is conserved. That's the first thing I'm saying. Second of all, I'm saying, note, let's go back to this page. Oh, and I have to see what time it is. Okay, yeah. Going back to this page, notice this kind of interesting thing. Whenever you assume that a system is like symmetric, when you assume that it's like reversible, what you really are, you're noticing something about energy conservation. Like if I throw something up and you take a movie of it, if I throw something up, like let something go in the presence of gravity, which is a conservative force. I throw something up, and let's even say you take a movie of it, and you even have a digital readout next to the object that tells you like the object's speed at every moment as it's going up, right? So it's like thrown up at 100 meters per second, and then like a moment later, it's like 90 meters per second, and then 80 meters per second, it's something like that, right? If I made a movie of this thing going up with the digital readout of speeds, and then I later on went up to you and said, I'm going to show you this movie now, but I'm not going to tell you. I might be showing you the movie forwards. I might be showing you the movie backwards. You tell me, right? You couldn't tell me. If I showed you that movie of something going up with all of its speeds going down, you would look at me like, yeah, that seems plausible. That could be a thing that was just thrown up. Like, seems reasonable to me. Or if I played it backwards and it was falling down and all the speed numbers were, getting larger and larger, you could look at that and be like, yeah, I mean, that could have happened. Something could have dropped. Whether I show it to you forwards or backwards, both cases would seem plausible, natural, possible. You'd have no way of knowing whether it was the actual movie or the backwards version of the movie, because the process is reversible. It is symmetric. Any process that conserves energy, can go that way, and the numbers will read the same way, and it can go back and forth that way, and you never know whether it's going forward or backwards. As opposed to put a hot cup of coffee on your kitchen table, make a movie of the steam rising out of the coffee, the steam traveling like up away from the coffee. Run that movie backwards to me, and I see steam being sucked into a cup of coffee, right? Or take a movie of a car going down the highway as exhaust comes out of its pipe. Run that movie backwards and we have a car going in reverse. Okay, that's plausible. But we have steam being, I mean, we have exhaust being sucked into a car pipe. Not possible. That never happens, right? Or even just like drop of like a vase, like drop your coffee cup, your ceramic coffee cup off your table, let it fall to the ground and smash into a million pieces. Make a movie of that. Run that movie in reverse and you have a million pieces assembling one another into a coffee cup. That doesn't happen. So in other words, those processes where mechanical energy is not conserved, where heat is being released or entropy is being increased or something like that, when mechanical energy is not conserved, the process is not symmetric or reversible in time. When you can tell the difference between a movie that was run forward and a movie that was run backwards. One is plausible, the other's not. When energy is not conserved. When energy is conserved, everything is symmetric in time. Okay, like the pendulums that you're doing in lab right now. They're just like this mass on the spring system. They are oscillators that are going back and forth symmetrically in time because they conserve energy. In this case, it's a spring force. In your pendulum case, it's a gravity force. But each force is conservative. The system is conserving energy. The system is therefore symmetric, reversible in time. In fact, I would even argue that the system is a clock. And we're going to talk more about that next week, but any system that conserves energy is not only obeying clocks, but is itself a mini clock. Okay, I'm just saying that. All right, I'm going to do one. We have 5 minutes. Okay. I'm just going to say, I'm going to write the answers to the next one and leave it at that. And then we'll meet again next week and I'll make more tracks. I owe you your homework still. I apologize for that. There's not any new homework for a while because I got to catch up with you. And I know I have to start catching up with the lab. But I'm just going to write the answers for the next questions so you see them, so you can see if you did them right or whatever. And we'll end on that note. So question. All right, so I'm just writing the answers. So these are not full proper solutions, but just so you can see. Okay, I'll explain this more next time, but I'm just writing the answer so you can see. A lot of you put that the jerk was constant. I sort of see maybe why they didn't show a lot of work. But I'm not saying this is easy, but these are the answers. The speed is going up, the magnitude of speed is going up, the magnitude of acceleration is going down, the magnitude of jerk is in fact going up. How could you possibly know that? Well, you might not know for a fact, but consider the pattern. I'm saying go back one step and think of what the position's doing. The position from 0.15 to 0 is going down. That's right. So if speed is, so position's like the function, speed's like the first derivative, acceleration's the second derivative. It seems like we have a pattern that's developing there, and we do. The jerk is going up, but I'll explain that more next time. And then I'm just going to say for question 9, I'm just going to say the answer. We're really going to have to get into it next time, but question 9 is long. It's going to involve a lot of class next time, but that's the question, right? believe the answer is. This has to be discussed a lot, but. I think the answer to this one is 0.116, is it? I'm suddenly having a brain fart, but I think. Wait. Yeah. No, what? No, I'm just saying. I actually don't. I think. Don't quote me on the answer, but just write this down for now. This is what we're going to pick up next time. I have a lot to explain about it. And if you did all the rest of the homework, but you couldn't do question 9, I totally understand that too. We'll talk about it, but that's all I want to say about it for the moment. I know it's been a very long class as usual. You've been very patient. You're being very patient with the homework. I appreciate it. I am done. If you guys are done, I'm going to hang out in case there's any questions or anything. So I'll hang out for a couple minutes, but I'm good or as soon as you finish copying the notes or whatever, I'm good. If you're good, you're welcome to say, and I'm going to turn off the recording. So thank you guys very much. No, yeah. No, I totally, yeah, goodbye. Yes, whatever things were due October 1st, I'm extending. Don't worry about the October 1st deadlines. I'm changing those. Don't worry about that. And thank you guys. And yeah, thank you. Have a good evening. Yes, wait, I'm going back. What, page 3? Wait, you have a good rest of the week. Can I refer back to question 3? Oh, like, can I? Sure. Question 3. I believe question 3 was. Wait, did I stop? Let me just stop the recording so no one.